I'm not going to read this word for word, but basically what we're talking about is removable discontinuity, jump discontinuity, infinite discontinuity, and oscillating discontinuity. So a removable discontinuity are like the two graphs that I have on the screen, and I'll zoom in a little bit so you can see them a little better. The reason there's a filled in circle here is that this function may be a piecewise function where it is not defined at 0, 1, but then we arbitrarily just plug the hole. We just said that when x equals 0, let y equal 1. So this is like a piecewise function. It's a removable discontinuity. Actually, we could consider this continuous, I suppose. But what we're more likely to see is this right here, which is a removable discontinuity. Now, I've seen some textbooks call them pluggable discontinuities, and one way to, if I put my thumb over it, can you tell? No, it's like I'm plugging the hole. Now, what a little more formal definition of that is that the limit as x approaches 0 is 1 if we approach from negative infinity. If we approach from positive infinity, the limit is 1. And so we have a two-sided limit. As x approaches 0, the limit of this function is 1. Now it's discontinuous because it's not defined, right? But it's a removable discontinuity because I can write another equation that will give me a straight line that goes through that point, and I could apply calculus to it, or just plug the hole. Another type of removable discontinuity is this example here. This is a removable discontinuity because again we could plug this hole if we wanted to. Now, one discontinuity that is non-removable, now we're going to talk about the non-removable discontinuities. Jump discontinuities. I literally jump from here to here. I can't remove that discontinuity because if I plug this hole, guess what? It isn't a smooth curve. It's not continuous. So this is what we call a jump discontinuity. It looked like our step function from the previous example, sort of. But I can't do anything with that with regards to continuity. It's non-removable. Some functions graph like this, where the limit as we approach a certain value blows up to infinity. You could flip-flop that and it'll blow up to negative infinity. This has a two-sided limit. As I approach from here, it goes towards positive infinity in the y direction. As I approach from this direction, it goes to positive infinity. So the left and right-sided limits go towards infinity. Therefore, it has a two-sided limit at x equals 0 of infinity. However, I can't remove the discontinuity. It's literally a jump discontinuity. I would have to jump from here to here. It has a horizontal asymptote at x equal, or a vertical asymptote at x equals 0, because when x equals 0, the denominator is 0 and then it's undefined. And I can't make it be defined. Because I can't plug in a 0 at all. I can't, not with that function. Now another type of discontinuity is an oscillating discontinuity. These are very rare, although you might see one of these on the test. The behavior of this function is wacky. And what happens, and this is what the graph would look like, but the oscillations in the period in between shrink and shrink and shrink and shrink. X can't necessarily equal 0 because then our angle for theta is undefined. So what happens is as we approach 0, we get some wacky behavior. It affects the period of the function, sort of. And we just can't, it's like a jump discontinuity. We can never ever plug in 0. We can't plug the hole. So we call it an oscillating. It has no limit as x approaches 0. Mainly because they approach different values. So what we could talk about is removing discontinuities, because sometimes we still want to apply mathematics And so let's look at the function f of x is equal to x cubed minus 7x minus 6, all over x squared minus 9. So there's a couple of ways to remove the discontinuity. The problem that we're going to run into is that this is a difference of squares. It factors to x plus 3 and x minus 3. Those are the zeros of this function, so we'll have problems when x equals 3 or negative 3, right? So x cannot equal 3 and x cannot equal negative 3. Well, wait. Well, it looks like they only looked at one of them. X equals 3. So the problem is I could just make a piecewise function and plug the hole. I could just say x equal when x equals 3, I'm going to evaluate the function at 10/3. And that's kind of like this. That's where you would get a graph that looks like this. You got like a curve and then a circle that's closed.
Let's plug that into your calculator.
Oh, this one you can't. You can't. Gotta use your noodle. Okay. Now we would, because it's defined at every x and y, in other words we can map every x to a y value, the function g is a continuous extension of the original function. Okay. So continuous on an interval, one more thing and then we'll jump into example 3. I had to kind of give you a precursor to what all the information we needed for example number 3. So what we're talking about really are continuous functions, and they could be continuous on an interval. And that's just we arbitrarily choose the interval. We select a chunk or slice out of the curve where we know it's continuous. And then we could talk about a continuous function, and that's for every point on the domain. And so if we look at this graph here, y equals 1 over x, it's a function, sort of. The problem is when x equals 0. I have a vertical asymptote. I can't do a whole lot about it, but I could carve out this chunk and we would call this the relative domain, and I could say it's continuous on this interval. So as long as I apply calculus concepts to just this portion of the graph, I'm good, because it's continuous for the part that I'm showing. Same thing over here. If I just pick out a little chunk of the graph, I could pretty much choose anything except for when x equals 0. But when I start to get towards x equals 0, all this calculus stuff doesn't work. Okay, does that make sense to you guys? So for example number 3, it's very important that we're able to identify continuous functions. So it says the reciprocal function of y equals 1 over x, that's the name of y equals 1 over x, is called the reciprocal function, is a continuous function because it is continuous at every point on its domain. However, it has a point of discontinuity at x equals 0. Because it's not defined there. So we still call it a continuous function because the domain is all real numbers except what? X equals 0. So not every function has all real numbers for their domain, but if a function is defined, and when I say defined, what I'm really saying is I can get a y value. So since the domain does not include x equals 0, all the other numbers work. Therefore, it's a continuous function. But I need to be aware of the function because when I go to do calculus, I can do calculus on this whole thing except x equals 0. Does that make sense?
Could you explain it one more time?
That limit, the formal definition of a derivative, will work everywhere except x equals 0.
Yep.
Does that make sense?
Yeah.
Okay.
But I mean the part of like why it's continuous. You said because it fits all the real numbers.
Well, a continuous function, let's look at the definition. Now in this, it's kind of a semantic thing, but it says a continuous function is one that is continuous at every point of its domain. What is the domain of y equals 1 over x? All real numbers except x equals 0.
Okay. Oh, So because.
Because the domain does not include
Because
0.
it doesn't have like a jump discontinuity in like the real numbers. It's still continuous even though there's technically like a space separating them.
Right.
Okay, that makes sense.
Yeah. Well, technically, yeah, it's just a term. Like there's labels, right? So like, I've heard some math teachers call this like a infinite discontinuity because the top goes to infinity and the bottom goes to infinity. This function is discontinuous at x equals 0, but formally, by calculus definition, it's a continuous function because its domain does not include x equals 0. It's kind of confusing, right?
No, that makes sense.
But really, for practical purposes, we can't do anything with it when x equals 0. That's what you really need to know.
Yeah, like, I get it, because if it were 0, it would be undefined, but if it were like discontinuous at like 2,
Right.
that wouldn't make sense. Okay,
Right,
that
right,
makes sense.
right. Good, good.